All right, welcome back to another episode of Science with Surback. Today we're going to be talking about section 5.2, which deals with quantum theory and the atom. So we start off here with a couple of objectives, and those objectives are to compare the Bohr and the quantum mechanical models of the atom. The second objective is to explain the impact of de Broglie's wave-particle duality and the Heisenberg-Uncertainty Principle on the modern view of electrons and atoms. And the third and final objective is to identify the relationships among a hydrogen atom's energy levels, sublevels, and atomic orbitals. So we begin here with talking about Mr. Niels Bohr. And what we had up to this point was that information and business about light and how light had that duality of acting as a particle and acting as a wave. Well, they could look at an emission spectrum. And they could see what colors that a particular compound or particular atom emitted. And so they could correlate some of that information. And so Mr. Bohr here was the first scientist to look at, okay, I know what I see here in terms of the emission spectrum of hydrogen. Let's go ahead, let's try to explain this in terms of electrons or electron behavior. So he knew a couple of things. Number one, the electron had to be somewhere around around the nucleus, around the center, and he went ahead and he said, okay, well, there has to be a circular orbit around that electron, or the electron has to have a circular orbit, and if it's not charged up or if it doesn't have energy added to it, it's going to be in this ground state. And so that ground state says, hey, the electron's going to occupy that lowest possible energy level. Well, then he went one step further and he utilized the business Mr. Planck talked about, and he talked about, hey, I can relate that quantized energy to the ground state or to that electron that hydrogen has. So what he did here was this. Overall, he took each orbit or each ring of the atom and he gave it a quantum number. Now, he said this quantum number is equal to the energy level. So what he said is, hey, there is rings or there is regions that I'm going to classify as energy levels, and I can place electrons in there. So when he referred to an electron being in the first or second energy level, now people could have an idea, well, where exactly is that, or have a depiction of where that was. And he also went one step further with this. Hey, the further and further, or the higher and higher energy level that an electron was occupying, the more energy it had. Now, also what he said is, hey, when electrons get excited, like we've seen them heated up and things of that nature, they are going to emit that photon, which can tie everything we talked about in terms of light in that last sections. So what he was able to do was distinctly and distinguishably describe what happens to hydrogen's one electron, and his theory, his thoughts on this were very, very good, except here, we'll learn in a second, there was one mistake that couldn't be used to apply to any other element. Okay, the other thing here is that when a atom gains or loses energy, it's going to go through, absorb that energy in that electron, and we see it emitted as light as the electron goes from a higher to a lower energy level. All right, so let's get to it. Why was Bohr's model unable to hold true in terms of explaining the atom, or particularly the electron structure. So Bohr said, hey, there's these rings, and he was perfectly able to account for this hydrogen emission spectrum based on all that information. But they went to that next element number 2, or helium, and the reasoning that Bohr gave to explain hydrogen's emission spectrum, these lines here, couldn't be used to explain the chemical behavior of helium. And they tried it for lithium, same thing happened, didn't work. Beryllium, same thing happened, didn't work. They went through as many as they could, and they couldn't apply those same things that Bohr learned with hydrogen. So here we go. We need one more model here where the electrons have to change. They can't be in these perfect circular orbits, and that's where we get this quantum mechanical model. Okay, so with the quantum mechanical model, they knew at this point that light behaved as a wave and a particle, and they could tie this business to an electron. Well, with the model that Bohr proposed, they said that, hey, an electron has to go in a circular orbit, but they couldn't explain some things. So now what they did is they're going to develop this quantum mechanical model. And they did this through a series of mathematical operations where they meshed multiple formulas together that they already knew about light, and they included some information they knew on the electron and the atom. So we get to the de Broglie equation. And this was the math that actually predicts how particles have those wave characteristics or move like a wave. So again, the big picture here, this is explaining, hey, electrons, because they're particles, can move as a wave, and we can tie it all together in this formula. Now, we're not going to do equations, but I do want you to know that this, de Broglie, he based this start of the quantum mechanical model on math, proven math that they knew about light and they knew about waves. So let's go a little bit further here. So now we know, okay, electrons are not moving in a circular orbit, they're moving like a wave. So again, we've gone from the circular orbit to now the electrons are moving in this wave-like pattern. Well, Heisenberg goes one step further. He goes, okay, hey, what I know about light, and combining that with de Broglie's equation, okay, yes, an electron moves as a wave, so it moves up and down like this picture shows here. But if it hits something or bounces off something, we don't know where it goes. And so he put a few things together, and again, he proved this with math. It's more so more data driven than what we have here. But he said, hey, it's impossible to know exactly, precisely where a particle is and the velocity. So we can't know both at the same time, and that becomes known as his Heisenberg-Uncertainty Principle. So what that means is, hey, we officially cannot tie an electron to that ring or that certain region. It could be in an area, but we're never going to say, hey, the electron is right there or it's right there. Again, we know, hey, generalize, it may be in this area or this region, but we cannot specify exactly where it is at. So now we go to one additional scientist here today, and we talked about here Erwin Schrodinger. So Schrodinger uses that knowledge from de Broglie and Heisenberg, and he says, okay, yep, the electron now moves like a wave because we've proven that through the light business, and we can't exactly know where an electron is, so it doesn't have that perfect circular pattern or perfect circular orbit that it always consistently goes through. But we can have an idea. We can have a generalized location where most of those electrons are. And so Mr. Schrodinger here, what he did was he said here, we can have a general idea, or we can have an orbital of where that electron may be. So the best way to explain this here of an orbital, which is just saying, hey, where is that electron's probable location, is by this perfect picture here. So here, all these little blue dots that you see on the paper are the probable areas of where the electron is. And you can see that as you get closer and closer to the center, this one electron, or the first electron, is most likely going to be right there around the circle in a spherical pattern. So let's tie all of this together. We've now proven, okay, electrons cannot go around in a circle, but they can be restricted, for the most part, to a certain region. And we proved that from the math of de Broglie, Heisenberg's uncertainty principle, and what Erwin Schrodinger just provided. He kind of pieced it all together. So now we get to this, and this is really the important thing for us. Is that we can now begin to regionize, or we can specify what electron we're talking about and specify it in a designated area. So we start out by talking about the quantum number, and this is related to the energy level of the orbital. So as we go up in energy levels, remember the electron is getting further and further away from the nucleus, the center. Now, again, as we increase this N, which is representing energy level, the number goes up and the energy level also goes up. What we call N is the principal energy level. Now, what we need to know is two things. Number one, an electron is going to try to occupy the lowest possible region possible, or the lowest possible energy level possible, and it has to occupy a energy level of at least 1. So let's go into details here, and let's look at this. And all we're doing here is we are classifying where an electron can be. So we, again, cannot precisely say, hey, there's an electron in that particular orbit. We can specify just the generalized regions. So the energy levels are very, very broad. Think about a hotel room with multiple stories. Well, that hotel room is going to have floors, and those floors can be represented by the energy level. Well, within the different floors, there's going to be different types of rooms. There's going to be all these different rooms, and we can specify those general locations of those particular rooms. So those rooms, or those sections of each floor of the hotel, can be specified by these sublevels. So all these letters are representing is a way to break down each area of a energy level. In other words, here, if we're going back to our hotel example, these letters of a sublevel represent a specific region of that hotel floor. So let's say we're on the second floor, and there's two parts to the second floor. There is the normal, we'll call that coach class, and there is the first class rooms, okay? So all this is doing is this is breaking down where the electrons can be. Now, we mentioned here with those dots on a paper that we can specify the region, and we can get into even more detail. We can show you what each of these sublevels look like. So again, the sublevel is just specifying, well, where exactly is that particular electron? And so we get into these ideas, and we'll expand on this in section 3, of an atomic orbital. So an atomic orbital is a 3D region that describes an electron's probable location. So again, backtracking here, we can specify the energy level of the electron, which is like the floor of a hotel room. Then we can get into the sublevels, which is a specific region on that floor. And then we have these shapes to even more hone in on where that electron can be. We are going to concentrate on 3 different orbitals of where an electron can be. We have an s orbital, which has a spherical shape, a p orbital, which is known as a dumbbell shape, a d orbital, which has these clover leaf shapes, and we call this the unique dumbbell here on the end, and then an f orbital. You can Google it if you really are interested in that, but it's a little too complicated here to put on the paper. Now, what I want you to identify, or what I want you to associate is, hey, this right here, these orbitals are replacing those rings where the electrons can go. So no longer think, hey, an electron has to follow that track or that circular path. They can occupy these regions, and they occupy the regions because they move like a wave. These regions can be broken down into further and further areas, so we can specify what energy level we're talking about and what specific orbital we're talking about, so we can have a generalized idea of the electron we are describing. So bottom line up front here is this. We are describing where an electron can be, and I want you to break the habits here of saying, hey, our electrons are tied to these tracked orbits or tracked regions, tracked areas in the atom. They can be in these generalized areas, and they're in the generalized areas because they move like a wave. The other thing I want to point out here is orbitals, whenever you see orbitals, can only hold a max of 2 electrons. This will play a role in section 3 when we start talking about electron configuration. All right, so let's sum this all up here with the end of section 2. So with our overall progress here, we can say that we have these energy levels, or these broad regions an electron can be for each atom. Within the energy levels, we have that sublevel that contains at least 1 orbital, if not more orbitals, as we see. The other thing, just some administrative notes here, is that you'll see, hey, this is a px orbital, this is a py, and this is a pz orbital. That is because we're dealing with 3-dimensional shape, and that's to show you the different 3-dimensional shapes of those orbitals. Again, these orbitals are found within the energy levels and are distinct regions in which an electron can occupy at that energy level. So all this is doing is it's honing in on where an electron can be, or a generalized idea or location. It's not saying, hey, an electron has to follow this exact path. It's just saying an electron assigned to one of these regions is going to be in this general location. Now, this will make a little bit more sense as we go through and as we start with electron configuration. We will assign our orbitals, and it'll be even more specific to be assigning where exactly these electrons can be of an atom. All right, I hope you have enjoyed this particular episode of Science with Surbeck, and if you haven't done so already, make sure you subscribe.